Hello and welcome to today's webinar from the Principal Solar Institute. Today's topic is solar-specific geotech and foundation design. We have with us two of the leading experts in the world on this topic from AquaSoli, Bob Donaldson and Jürgen Schmid. Bob Donaldson is the Vice President and Project Manager of U.S. Operations for AquaSoli. Since 2003, they have completed 10 gigawatts of solar-specific geotechnical foundation design, risk assessment, and foundation failure remediation. In the past 2 years, Bob has worked on over half a gigawatt of solar site assessment, risk evaluation design reports for projects up to 90 megawatts. Also, we have Jürgen Schmid. He is the founder and CEO of AquaSoli, a highly experienced professional geotechnical and civil engineer, and Jürgen has completed the geotechnical engineering for approximately $1 billion of installed solar in the U.S. and Canada alone. AquaSoli is headquartered in Germany with offices in Boston, San Francisco, Amman, and Tokyo, and it's worked on almost 10% of the world's total installed ground mount solar capacity since the year 2003. And AquaSoli's solar-specific geotechnical engineering, foundation design, risk assessment, and failure remediation supports 10 gigawatts, or $12.5 billion of solar investment worldwide. And with that, I will hand things over to Bob. So, Bob, you can begin.
Thank you very much for the introduction, and thanks to the attendees who have committed their time and experience to considering the benefits of modifying the U.S.'s industry's standard approach to geotech and foundation design. I'd like to reiterate at this point that there's dessert for this presentation. Jürgen Schmid will be presenting photos and 10 years worth of lessons learned from solar foundation failure remediation. Those are great photos and very interesting topic. So I reviewed my notes this morning, and I realized that I managed to talk all around my topic without ever giving a simple statement of the issue and the value proposition. So here it goes. From a solar design standpoint, there's a huge difference between tasking a geotech to go out to your site and drill a few holes and then describe what he finds in the holes, or giving your geotech a mandate to find all the issues on your site that will cause problems for solar deployment, and then design a foundation that will address those issues. And oh, by the way, the geotech will be responsible if the foundations don't work. The value proposition is that once the geotech has been all over your site, they'll know it so well that they'll also be able to provide valuable input to everything from project planning to material selection and design, and that their input will lower the cost and reduce the risk of foundation failure throughout the entire project. So on 44 projects I recently analyzed, from 700 kilowatt to 80 megawatt, 70% of them suffered geotechnical related issues. And these issues ranged from, simple inadequate geotech and foundation change orders, or foundation installer change orders, to facility damage due to foundation failure. My message today is that these geotechnical project defects are avoidable, that they stem from the way we approach geotech in the U.S., and that the specific experience of a solar geotechnical specialist can help reduce project costs and increase value, and at the same time, their experience can significantly reduce solar foundation failure risk. Why bother with solar geotech? I mean, the fact is that geotech's cheap, and foundation, the total installed cost of foundations and geotech are small compared to the rest of the project. But the bottom line is that there's a lot more at stake. And what's at stake is that 60% of a project's installed cost and 100% of its production capacity is supported by solar foundations. If those foundations fail, the cost of project remediation can approach 100% of facility value. Who cares? Well, the entities who care should be the ones that have the most skin in the game. Those who are putting up money in anticipation of reliable returns, and the ones who are trying to own and effectively operate these facilities long term, and also the ones that are on the hook and risk having to pay for damages and repairs. So I'm going to offer you a case study which I really like because it clearly demonstrates how geotechnical issues can multiply through other project tasks and culminate in major facility damage. In this case, the cause of the issue started with the geotech. The geotech did not adequately characterize the site. The resulting foundation design was not suitable for site conditions. The civil work to remove foundation obstructions compromised the soil bearing capacity through the embedment depth of foundations, and the civil design didn't follow the geotech's recommendations for site dewatering. To compound this, the foundation installation procedure damaged a foundation design element that was meant to reduce frost adhesion. And construction during installation of foundations and racking impaired the drainage. Heavy fall rains flooded the site and saturated the already weakened soils. A series of freeze-thaw events during the winter caused 60% of the foundations to fail through frost heaving. The remedial investigation and design costs were around $200,000, while the estimates for foundation remediation approached $4 million. So a number of what-ifs come to my mind when I review this project, but a couple of points are very clear. The fact is that every element that contributed to foundation failure was in the control of project design and execution except the weather. What was missing in this project and many others is a strategy to integrate comprehensive solar geotech across all geotech-dependent project facets. So what's the root of the problem? You don't have to listen to me. You don't have to take my word for it. Just ask an installer. And the installers will tell you that the largest and most preventable source of project delays and cost overruns in their experience is geotech. The fact is that if geotech doesn't characterize the site properly, then third-party foundation designs don't address site conditions either. They either can't be installed as designed or don't meet design loads. Installers respond to RFPs with poor geotech by either increasing their bids by 10%, as much as 10%, or they simply don't respond to the RFPs. Meanwhile, the project impacts can be installer change order claims that typically approach 25% of the installer's contract value, geotech-related project delays, which typically can run up to 2 weeks, and additional foundation costs either from changes of design or changes of material. By the way, as an example, the boulders that Jürgen is standing by weren't adequately identified on this site by the standard geotechnical approach. But I assure you, the foundation installer found them, and it seems like he must have found every single one of them. At any rate, what goes wrong with geotech that it's not adequate to properly assess site conditions? The problem really is that a geotechnical consultant can't adequately assess a site and scope a project on the budget that's often provided to do the work. Site developers have limited money to spend, and the budgets they spend determine the scope. In addition, site developers often have to rely on locally sourceable geotechnical consultants to meet their budget requirements, and those geotechnical consultants may or may not have solar-specific experience. In addition, the equipment and procedures that are used for our standard site assessments are borrowed from other industries, and they may be poorly suited to recovering and quantifying critical solar-specific site data. The limited budget, limited scope, low sampling density, and limited data recovery translate to inadequate site characterization. Compounding the issue of solar geotech, third-party foundation designers are often responsible for the foundation designs, and these third parties have no site-specific experience whatsoever. They have to derive their design parameters from the limited geotech, and as such, those design parameters are twice removed from actual site conditions. The site assessments don't often provide adequate data for foundation optimization, and the actual designers are not liable for the performance or the installability of their foundations because they're based on the work provided by others. However, there's an alternative geotechnical approach, and that is to contract a solar geotechnical specialist to perform a solar-specific site investigation. This approach pretty much amounts to a treasure hunt for solar site specifics. The objective of the treasure hunt is to add project value by finding and quantifying site solar design specifics and cost-effectively applying them in project design. The result of this approach is to reduce project costs and foundation failure risk. A solar-specific geotechnical approach of this kind integrates site research with soils investigation, analytical load testing, and site-optimized foundation design. It's best if it also includes providing quality assurance and quality control for foundation installation. Remote site research is conducted to preliminarily characterize the site and identify potential solar specifics. This makes it possible to design a field investigation specifically to fully characterize those solar specifics. And in addition, it makes it possible to pre-design foundations for testing which accurately reflect site conditions. The physical site investigation employs specialized techniques to recover solar-specific design data. Those techniques include high-volume test pitting, which puts your geotech up front and personal with the soils. In this case, the standard geotechnical site assessment missed the fact that 30% of the site was a construction and demolition debris dump. The installer, of course, found the issue, and the test pitting survey really made it clear what was down in the ground. The approach of test pitting accurately characterizes changing soils and their engineering characteristics both horizontally across the site and vertically throughout the foundation embedment depth. In concert with the high-volume test pitting, analytical foundation load testing is completed, which directly measures soil's bearing capacity, and in the same process, tests foundation installability. The benefit here is that foundation design can be based directly on measured soil's bearing capacities, so that foundations can be optimized for specific soils conditions. In the end, foundations can be optimized for installability, the cost of materials and installation, of course long-term performance, but they can also be optimized to specific rack design features. Well, in the opening case study, I hope I demonstrated that many project tasks are geotech dependent. And a solar geotechnical specialist's input can add value to many of those tasks. In general, those tasks also impact the cost and reliability of solar foundations. And those tasks include site vetting based on geotechnical issues, site selection, of course the solar-specific geotechnical investigation, preparation of bid packages, rack selection and layout, and civil issues along with quality assurance and quality control for installation, and O&M, operation and maintenance plans for long-term operation. On the most basic level, your geotech's input can be leveraged to improve bid packages. Their input can add accurate site characterization, provide a proven installable foundation design. They can define and give you quantity takeoffs for change of soils conditions and provide engineered foundation design alternatives and quantity takeoffs. And finally, they can offer specifications for installation and quality assurance and quality control for installation. In this manner, they can reduce foundation installer uncertainty and level the bidder's playing field, lowering bids. But more importantly, most importantly in fact, foundation installation controlled in this way reduces foundation failure risk. In other ways, the geotech's experience can be used to optimize material selection. For instance, selecting a racking system that's well adapted for your site soils, and site terrain can reduce foundation costs, increase deployable area, and reduce site prep and restoration. If rack selection is poorly suited for a site soils, foundation costs can be tripled. As an example, if a racking system is selected for a site and the foundation design requires a total pile length of 13.5 feet, an alternative racking system that requires piles of 12.5 feet or less can cut installation costs for foundations by as much as 200%. The reason this occurs is because the longer foundation or the longer pile length requires specialized handling, and the installer has to source expensive and hard-to-find installation equipment. Similarly, a selection of a racking system that's well suited for your site terrain can increase deployable area by 30% and site prep and associated restoration costs by as much as 70%. In addition, your geotech can add value-added input into various design features. For instance, he can help organize and coordinate civil design so that racking specifications are followed to minimize site prep and restoration costs. He can ensure that construction and sequencing is coordinated with foundation design such that the foundation design can consider soils disturbed by grading and the site work adheres to recompaction specifications. He can review and provide input on drainage and dewatering design to prevent soil saturation and coordinate civil design with array layout. This is important because in a few cases I've actually seen racking laid out through retention ponds, and in one case the retention pond was underlain by frost-susceptible soils. And in addition, he can help prepare the O&M plans for future site operation to support foundation reliability. So I keep on talking here about adding value to projects. Let's look at some of the potential project impacts. These are for a 10-megawatt project with a total cost of $21 million. Your geotech's input can reduce bids by 10% for racking and foundation installation, can reduce installer change orders by 25% of their total contract price. He can reduce foundation installation costs by 100 to 200% and site work at a rate of $10,000 an acre. So the potential savings are $1.8 million. But let's say, for instance, that I'm way off and that actually only half of those costs can be realized. So the kicker here is that the incremental cost of the geotech, which provides these benefits for a site of this size, is about $15,000. That is to say that besides the cost of a typical site assessment, $15,000 in addition buys a solar-specific site assessment. The cost increase is driven primarily by adding analytical foundation load testing and optimized foundation design. So for an investment of $15,000, the potential project savings of $900,000, which is a return on investment of 6,000%. There's some additional advantages. The increased deployable area and production potential, as I said, of up to 30%, reduction in potential project schedule delays, and most importantly, 100% of the facility's value is at lower risk of foundation failure. My final point today is that the same specialized solar-specific geotechnical experience that can reduce risk in new project design can also quantify geotechnical risk built into existing facilities and shovel-ready projects. This approach is a stepwise process. It starts with risk screening, which is a benchtop exercise to review risk indicators, which may include the experience and the scope of the geotechnical investigation, foundation design, and perhaps the foundation designer's experience, the quantity and quality of any load testing conducted on the site, construction sequence, and geotechnical or foundation-related change orders. If risk screening indicates risk, then stage 2 is a site geotechnical risk investigation, which really is an in-depth design review covering geotech, foundation, racking and layout, civil and site work. It includes analytical load testing of project foundation designs and load testing of selected as-built foundations. In step 3, risk mitigation design, risk is quantified and alternative mitigation strategies are identified along with risk-cost-benefit analysis. These mitigation strategies can be financial or engineering. Financial mitigation may include bonds or additional insurance. Engineering mitigation strategies may be as simple as improving site drainage or installing dewatering systems. They may include structural modifications to racking or foundation reinforcement. The main point here is that mitigating foundation risk as part of property transfer negotiations is far and away preferable to remediating foundation failure at some unknown future date. So I'm going to close with a couple of recommendations. If you need motivation to approach geotech in a different way than we typically do, consider the value proposition of solar-specific geotech along with its incremental cost and compare that to the cost of remediating foundation failure. If you're hooked on it, then implement solar-specific geotech at the earliest possible time to provide more accurate basis for project planning and design. In every case, establish a strategy to ensure that geotechnical considerations are integrated into geotech-dependent projects throughout the project, and leverage the experience of your solar geotechnical specialist for value-added design input. Always apply rigorous QA/QC to foundation installation and screen for and assess geotechnical risk as part of property transfer negotiations. So now for dessert. I'm going to pass the presentation on to Jürgen. The first thing you'll see is some interesting foundation failure issues. Thank you very much.
So thank you, Bob, very much. Dear ladies and gentlemen, welcome to my part of the presentation. I will be briefly talking about typical damages I've seen in my 1 decade experience with solar farms. And yeah, well, since it's always better and it's always less painful to learn from damages of other people than to fall into the same traps, we're here mainly talking, of course, about ground mount solar farms and ground-related risks. I will show you some pictures from worldwide damages, and I will describe briefly the causes of damages. In this case, for instance, on an island in the Atlantic Sea, the longitudinal bar was much too weak, though a winter storm resulted in failure of the foundation, and as a consequence in a failure of the racking structure, including tilting of piles. The causes were additional to the fact that the longitudinal bar was much too weak. Also, a loss of soil due to erosion had happened, and the piles were being uplifted due to a loss of the tensile bearing capacity and a weak longitudinal beam that was too weak to provide a sound load distribution between the foundation posts. During the erection of the farm, no quality control was put in place. And also another thing was no load test in this part had been made, so the merchants of the building owner thought they were very clever to let the geotechnical company only working at the first section of the farm, and at the second part they would assume the building ground to be the same and to proceed without any geotechnical consulting to spare money. But the failure revealed that the building ground conditions differed between both sections, and furthermore, no compaction control was in effect in areas of earthworks with cut and fill. The effect was a catastrophic failure of module assembly. Clamps opened, modules flew up to 600 feet away and smashed into other PV modules and into house walls like tomahawk axes. Luckily, no human was being hit. Nobody was injured.
Hey, Jürgen, you need to advance your slides if you can.
Yes, I will go to the next picture now, to the next slide. So this would have been in a film. I cannot show it here, but what you would have been seeing in this film is that the system would come up here, up and down, swinging, up and down under wind impact. This is a pre-film from a similar case of misplanning where no damage happened yet since the plant has been recently built up and no storm has happened yet. But now the mounting system manufacturer asks us to assess the risks of failure and to recommend countermeasures to avoid any damage. In this case, also like in the case firstly shown, the axial distance between the piles is too long in relation to the bearing capacity of the piles, and the stiffness of the piling and the longitudinal bars is too weak. As a consequence, during storms, the system builds up dynamic behavior. Conventional civil engineering rules assume wind loads to be static. With the impacts becoming dynamic, the steel parts, aluminum construction parts, and the foundation will be impacted dynamically in cyclic periods. The result is a much higher impact onto the foundation with increasing plastic deformations and the risk of fatigation of underground and metal construction. So now I go to the next slide. The slide in this case shows there was no soil investigation program and there was no quality management set in place that would have detected construction deficiencies. The construction company simply got the signature of the building owner after completion of the site on the delivery documents without any objections. A few months later, this lacking diligence resulted in a failure of the foundation. In this case, 2 5 to 10 megawatt plants have been erected on slopey hills, on slopes, on each one at a southward inclined slope. Prior to installation, the whole vegetation was cut off. Plant roots, which would offer erosion protection and slope stability, at least at the surface, were being removed. The building owner was strongly invited by the planners and the project management to induce a slope stability analysis, but the building owner remained deaf and dumb and decided not to do so. At the end of the construction phase, during transition from winter to springtime, heavy rainfall occurred over weeks, and as a consequence of soil saturation with water and destabilizing forces induced by downstreaming water, a landslide of the surface was provoked. The piles were still stably standing at their original place, but the soil at the surface had moved downwards, dragging it with it all the wires and cables. Even 1 year after the plant completion, the plant was not yet connected with the grid due to this damage. So you can imagine this resulted in a really very high material damage and a hurting loss of feed-in tariffs. These are further examples where in the first case, in the left picture, a slope failure happened. You can see that in the background, at the green meadow, with grooves and moats in the background. And furthermore, you can also see local and differential uplift due to frost upheaval forces and due to swelling of tropical cohesive soils could result both in similar Euler waves like depicted in this photograph at the left side. At the right picture, you see erosion that could harm the foundation and of course also the cabling if progressive. Another field are landfills. Also landfills hold risks of sliding, especially the boundary surface between natural soils and geotextiles or geomembranes may be slippery. Prudential, sound engineering should avoid surprises. Whenever solar farms are being set up at landfills, the planner has to have in mind also the interaction between solar farm and water household of the landfill liner system, especially if mineral liners or geosynthetic clay liners are being used as a sealing layer. Quite often we come across projects where the risk of water level changes has been ignored. But the water level has a strong impact on the pile bearing capacity due to uplift forces, but also due to a loss of cohesion of water-sucked soils. So, for instance, if the pile load test happened in summertime with a deep water level significantly below the foots of the piles, then in this case the water level in wintertime might raise, leading to a loss of 30 to 40% of its bearing capacity it had during the load test in summertime, or might result even in a higher loss of bearing capacity. This loss is significant, and this loss is not covered by the safety level offered by the usual safety factors. So what could also occur is differential settlements, and due to seasonal water level changes might lead to erosion of bearing soil and reduced uplift capacity. As an effect, severe undulation along module rows could appear, resulting finally in a failure also of the modules due to bending. If risk of seasonal change of water levels are being ignored, differential settlements and harming of PV modules may occur. The flotation forces lead to a lack of bearing capacity and to erosion of bearing soil. In manifold projects worldwide, we encounter inhomogeneous soil situations due to prior use as an industrial or military facility. Bombing in the world wars, like at this former NATO airfield, left bombed craters in the landscape that were simply filled up with loose soil. These loosely refilled bomb holes normally would lead to higher amounts of cost due to concreting instead of pile driving, but we developed a quick test method to quickly determine the bearing capacity of nearly each pile during the construction phase. So thus we were able to limit areas which require technical extra measures to raise the bearing capacity, and thus we significantly reduce the building cost. Noise protection embankments are often used as landfills containing thousands of cubic feet of concrete, rocks, bricks, and other construction site waste. To avoid financial damage by unforeseen raise of cost, a diligent soil exploration with test rammings is strongly recommended. It is better to avoid change orders by soil testing in an early stage of the project. Change orders regularly result in delays and cost explosions during the erection of a solar site. Besides, soil inhomogeneities can also lead to differential settlements, which have to be addressed by an appropriate draft design of the solar mounting system, for instance, the length of the tables. These pictures here show typical results of hindrances hit in the underground. These ignored ramming hindrances may lead to a shockingly high change order cost and delays of construction. So you can say, to design a mini-pile foundation, you urgently need test loadings for two reasons. The forecast of the bearing capacity, of course, of mini-piles, just based on soil parameters like the friction angle and cohesion, would not be reliable enough due to extremely scattering properties of the soils close to the surface ground level and due to climatic impacts. And the second reason you may guess is, you have a look at these pictures, also the feasibility is essential to be tested just in time before the profiles are ordered in a number of thousand profiles or more. But even with test rammings, of course, that has to be honestly said, unobstructed execution cannot be guaranteed to 100%, but is much more likely to achieve an unobstructed construction phase by performing test rammings before then ignoring risks and starting with installation without priorly performing any test rammings and load tests. Lacking quality of embedding of piles is also in some cases a big problem. Lacking or insufficient installation equipment can be one reason, but also lacking quality control during pile driving. This negligence may end up in risks of module fishes. This slide here shows no swimming bassin. Now, in this case, the surface was dry and very firm in summertime. One could easily access the construction site by using a two-wheel driven car. But when the construction site was started in wintertime, rainy season started and kept on raining and snowing for several weeks. This, in combination with heavy traffic of construction companies, led to a destruction of existing drainage pipes and trenches. As a result, the whole area was flooded over weeks. The soil was fully sucked with water, and the initial firm soil got mud. This led to a redistribution of forces within the whole construction and a redistribution of the forces to the front piles, and finally ended up in a break of the weld seams between front pile and upgoing construction. Finally, the whole mounting system structure got kinematic and had to be repaired. Many piles had to be replaced. New pipes and an entirely new drainage system with drainage ditches had to be rebuilt. However, the high cost pressure sometimes leads to dog's dinner, resulting finally in an even higher cost, including all the fixing costs, compared to if a sound engineering would have been put in place right in time. So, the sound engineering has to take the care about installation of a properly working drainage system and or risk of flooding, avoiding dramatic changes of soil conditions, finally resulting in high failure risk of foundation and metal construction. To preserve a long-lasting construction, also the corrosion potential of soils has to be determined and to be regarded during planning. This will be performed by measurements of the electric soil resistance as well as a determination of chemical soil parameters in the laboratory. These results may be evaluated to assess the risk of surface erosion and of pit corrosion. If indicated according to the examination results, protective measures have to be undertaken, like additional coating to avoid a loss of investment values during the usual 25-year term of operation of the solar farm. We expect that solar farm constructions will be furthermore used even after a 25-year period and operation for a prolonged period if the plant is well engineered and constructed and the steel material is sufficiently protected against corrosion. These pictures here have been taken not anywhere in a developing country, but in a rich country with sound engineering, normally. In this case, no geotechnical survey had been done and no foundation engineering. So we got a phone call by an unknown company, until this point. They asked us, please, may you write the geotechnical expertise, and then date it back to a date before of this damage. I asked him, no, of course, explain this to your insurance company and put every card onto the table, put the full cruise onto the table. And then half an hour later, we got a second phone call of this guy, and finally he ordered the soil exploration and the soil expertise for the insurance company. This happened to this client at 2 locations and resulted in a financial damage of $13 million in total. In this case shown here, we are very proud that we got a phone call by an excited client who told us we had a snowstorm and all the surrounding solar farms have damages now. Only our farm designed by your team, by your engineering team, has not been harmed. We strongly recommend your team for design of ground-mount solar structures to reach safety of investment. So he sent this corresponding pictures, like this one indicated here, to banks, investors, and insurance banks, which was pretty good advertising for us, of course. So having this all in mind, sound engineering is essential to receive sustainable investment with sufficiently long-lasting mounting structures and foundations. In the following few slides, I will show you some examples before I come to an end of my presentation. And, well, let's look at this slide here. This military airfield in northern Germany has been used for 8 decades by military aircraft, first by German Wehrmacht, then by the Allied forces, and later by NATO. The famous German rocket engineer Werner von Braun launched here his rocket aggregates. After World War II, Werner von Braun settled over to the US in a secret program to set up the first US short and middle range rocket development programs. Around millennium, the airfield now has been converted into a peaceful solar facility with 82 megawatt of ground mount solar. Due to the heavy bombing of the airfield in World War II as a development site for short-term rockets, we encountered there many loosely refilled bomb craters, which were, of course, a hindrance for our installation of solar farm here. So, for this 82 megawatt solar farm, we developed a quick load test method to quickly test nearly every pile in the field. Thereby, we avoided hundreds of thousands of cubic meters of concrete and saved 20 miles of steel. At the same time, we reached a safe and sustainable construction that should last for decades, delivering the inexhaustible amounts of electric solar engine energy. Here, at this place, we are working on a long-term comparison between 2 different solar mounting structure systems, measuring wind forces and the corresponding deformations in the mounting systems over a period of at least 10 to maximum 25 years. This research program is still ongoing. So I come to my last slide. This is an example for a 25 megawatt solar installation at a waste deposit. It was ground mounted on earth screws. And for this $300 million invest of a 250 megawatt solar installation at the location of a former nuclear power plant and construction site, we delivered the foundation engineering and the due diligence analysis. Furthermore, we provided an expertise for improved dewatering installations, drain pipes and ditches on the site. Last but not least, there were nearly 100 miles of trenches opened by archaeologists where we delivered the recompaction control. Thereby, we achieved to avoid concrete foundations and could take simple steel piles that save the client several million dollars of foundation costs. So thank you very much for your attention. I'm at the end of my part of the presentation, and I might say my sincere thank you for your attention, and my thanks also to Bob Donaldson and to the organizers, to Matthew and to Rick. And yeah, I hand over back to Bob Donaldson, who is leading our AquaSoli activities in the US and the Canadian market. Thank you, Bob.
All right, great. Thank you very much, Jürgen. We have some questions coming in, and again, for the attendees in the audience, please chat your questions. The chat window should be in the lower right corner, and you can send the chat to all panelists if you want only the authors to hear see the question, or to all participants if you want to share the question with the entire audience. So the first question came in from William. His question is there an industry-wide definition of who qualifies as a geotech, such as licensing, degree of education, and are there standard designations for someone who is qualified to be a geotech?
Jürgen, you want to take that?
Yes, of course I can do that, and you can also supplement the US the corresponding information. Of course, there are worldwide lists for each company of registered geotechnical engineers and civil engineers, civil engineer professionals. But the thing here is that the solar farm installations have a very brief history. And what we in the beginning, what we did was, of course, we tried to transfer our knowledge of foundation engineering of deep piles used for skyscrapers or for any high buildings. We tried to transfer this knowledge, of course, to this new field of application. But what came out is that there are some specialities on this field of engineering, since our piles are very short. It's the demand is here to engineer a high number of very small piles, and these small piles are somehow sometimes underestimated, or the necessary skill to provide these small piles, because the forces are very low compared to big piles, and so many of the geotechnical engineers, they underestimate the need for optimization, and they underestimate also the influence of the climate, since we are here within the first 6 feet of the top, so including the topsoil, and so the stiffness of the soil is decisive also for the long-term behavior of the foundation, for plastic deformations, for fatigation, and so on. So we have a lot of specialities that you can say it's not sufficient to say I will just take any geotechnical engineer or any civil engineer who is registered at any list there in a national list, but you have to take someone who is really experienced with this solar-related special risks related with the installation of piles very close to the surface, to the top surface.
Okay, excellent. Next question was from Matthew. Are there different geotech requirements for a tracking PV system versus a fixed tilt?
Well, that really depends on the soil conditions. You know, the various different types of racking drive various foundation requirements. You know, for instance, a tracker mounted in bedrock has a much different foundation design than a tracker designed for soft soils. So you really can't answer that question without knowing more about the soils. You know, tracker foundation design is similar in every way to design of foundations for fixed mount systems, except you have to take additional dynamic design considerations into the design.
All right. Next question came from Stephen. It was directed to Jürgen, but either of you can answer. What investigations would you recommend to properly assess the corrosion potential at a site?
Yeah, we do soil sampling, of course, of the topsoil, because on the first hand, the first 1 to 2 feet are decisive on the long-term behavior, because there is a a strong exchange of air, of oxygen, of water, of course, of rain, precipitation, and there you have also humid acids. So we take samples, we give them into chemical soil laboratories, and we do electrical soil resistance tests on site. These are the two methods or the two ways to gather the necessary information to evaluate the corrosivity potential of a soil situation.
Okay. Next question was, do you have any thoughts on a 12-megawatt system to be installed on a brownfield? Just what sort of general concerns would you have?
Well, sure. I can address that. It starts off with a very, very pertinent question about your regulatory officials in the area. And also the character of the brownfield. I mean, the easiest answer to that question is put the facility on ballasted foundations so that the soils aren't penetrated. But then again, it depends on the character of the contamination in the brownfields. Some contamination really just doesn't have a route of public exposure, so it doesn't matter if a brownfield is penetrated. And others will, of course, require, the regulators will require that the surface of the brownfield not be punctured at all. So yeah. Brownfields are a great area for solar deployment, but the answer to your question is it depends on regulation and it depends on the type of contamination present.
And I would also like to add, yeah, brownfields, like you said, is a very good location, and we have an experience of 36 project examples with brownfields and landfills. And what you have also to draw attention to is, of course, the amount of differential settlements. So the table length has also to be attached to the expected amount of differential settlements. If you have always total settlement, which is not harming, not directly harming, but related to this total amount of settling, you have also differential settling between the piles. So there has to be a close interaction between the geotechnical engineer and the construction engineer. We have both in-house here, also someone who does the steel mounting structure calculations and also the works hand in hand with the geotechnical engineering part. So, but if you regard this, differential settlements, brownfields are a good place to set up solar farms, of course.
Great. And a follow-up question about that 12-megawatt size. Is there a lower limit in megawatt size when you need to have a geotech study performed?
No. I mean, any foundation system for any size system can fail. And any foundation failure, no matter what the size of the project, is very expensive. The requirements for solar geotech is independent of project size unless you are willing to put up with the risk and the cost of potential failure. It really all depends on properly evaluating the site soils and then doing a proper foundation design for those soils.
Okay, next question was from Jobin. What about the pull tests? Is that a must, or can we solely depend on geotech?
Yeah, for very small, very small sites, like 500 kilowatt site, we have also special methods developed that allows us not to bring a big pile driver installation equipment to the site, because that would be too cost intensive. But for plants starting with a range of 1 or 2 megawatt, we strongly recommend to bring a pile driver to the site. For small size, you can also keep the pile driver machine on site and do your foundation design very quickly due to the small number of posts you need. And for larger utility scale for solar farms starting with 2 megawatt, 4, 5 megawatt size, of course, there's a certain delivery time to wait for the posts, for post delivery. but therefore I also would strongly recommend not to be shy with the cost for the pile driver machine, because this will avoid a lot of risk potential for damages and for cost optimization potential.
So let me add a couple of things to that. The issue with relying on geotech only is that the geotech that's usually provided is not adequate to fully characterize site conditions. That means that any foundation design that relies on typical standard geotechnical site assessments runs the risk of completing a design that really isn't suited for site conditions. On the other hand, if you do load testing, and we're talking about cheap money here to add load testing to your geotech, you actually measure directly the soil's bearing capacity, and you do it in enough places across an entire site that you fully characterize the change of conditions across your site, both horizontally and as well as vertically. So the answer to that question is, if you wanted to stay in the ground, pony up the money for the pull tests and load testing, analytical load testing, as opposed to standard pull testing.
Great. The next question is from Gary. What additional requirements would you recommend for the installation of carports or covered parking?
Jürgen, that's one for you.
Yeah, there are no additional requirements. I mean, in this cases, you have sometimes already a closed surface with concrete or with asphalt. We have developed techniques also to perform pile installation in these situations, and we have also had to develop new carport systems for 3 different market-leading solar companies. So we have enough experience for that, and there's no special requirement really differing from normal utility scale solar farms. It's all within the scope of ground-mounted systems. Of course, you have sometimes also high bending moments. So in this case, also we try to plan and to design groups of piles. For instance, 2 or maximum 3 piles in one row, which will be connected by the construction of the carport itself to bear the high bending moments due to wind load. But in principle, it's the same like the ground-mounted engineering of solar farms on a green field with piles.
Excellent. And the questions have been really coming in. We've actually reached the end of the hour, but I have time to stay on for a little bit longer. And Bob and Jürgen, would you be able to stay on to answer these questions?
Of course, yes.
I can. Yeah.
We will.
Okay. So I'll just let the audience know, if you've run out of time, you can disconnect at the end of our hour again. I'll keep the recording going, and we will post the recording later on today, along with the audio and visuals of the slides. You'll be able to watch those from the end, from the 1 hour mark on, to see the rest of the questions. And in the meantime, we'll just continue with the recordings, with the questions. So the next one is from Peter. His question is it a safe assumption that after receiving a full geotech study by a licensed engineering company and following their installation criteria, but then there still is a failure in the solar array racking, will that liability be covered by the geotech firm's liability insurance?
Yeah, that very largely depends whether the company had enough experience also with solar foundation design, if they knew about the specialities of designing solar farms and with very shallow founded pile foundations.
You know, in some cases, after you finish reading the geotechnical site assessment report, there's disclaimers, and the disclaimers say that, you know, they've done their best, but nobody can be fully cognizant of everything that's underground. And if you run into problems, then you should come back to the geotech and get them to do further investigation. Now, the foundation design is based on a geotechnical report that's already providing limitations to its applicability. So the foundation design is based on work provided by others, and the foundation designer therefore may not even have liability for the performance or installability of the foundation. So your question really, you know, in many cases, it doesn't look like the geotech will have that liability.
And the follow-up question was with AquaSoli, how does your reports look and your insurance coverage?
Yes, as one part maybe you can answer, Bob, and I can also add something. Do you want to start, Bob, or shall I?
No, I'm going to listen to you handle this one,
yeah, okay.
And I'll add what I can.
We have a professional liability. I think with doubling of the amount, and I think the total amount is around $4 million for material, and for damages, and also I think $4 or $5 million for damages or injuries, yes, for injuries or death. As I showed you on one of the slides, it's not really very unlikely that you could also have insurance that you could have also injuries of persons. Normally, of course, someone thinks if a solar construction fails, yeah, normally it's very unlikely to have damage of persons. Yes, if it's on a remote, if it's on a field very remote from a village, it's very unlikely to have a personal damage, of course. But as I showed you at one slide, with the modules flying around, you could also have injuries of persons, of course.
And I think so that was clear. I wanted to make sure that in the scenario that Peter had outlined, where AquaSoli came in, did the geotech study, and all of your criteria and recommendations were followed by the construction, and then there were a failure later on, it sounds to me like you would cover the liability up to $4 million. Am I reading that correct?
Yes, this liability covers any engineering failures, any design failures. If we made any mistake, that we did not do enough testing, or that we miscalculated anything, of course, that will be covered by this insurance. Yes.
Yeah, so if you've done the investigation and you've done the foundation design and you've provided the specifications for the installation and done QA/QC for the installation itself, it's tough to dodge that liability. So.
All right. Next question was, how long does a geotech study require? How long will you be in the field? And how long until the final report is ready for the rest of the construction process to use?
It depends on the size of the site. You know, I've committed to providing geotech for one racking company with a turnaround time of no more than 4 weeks for a final report. So from point of receipt of order, the stamped foundation designs returned in 4 weeks. As far as being out in the field, to a large extent, it depends absolutely on the size of the facility, but also the complexity. I will say, however, that in many cases we can complete the site investigation for something up to 10 meg in 2 days. So, you know, you can work it from there. It's tough to, you know, virtually any size site requires at least 1 day, but in many cases we can complete site assessment in 2, maybe max 3 days for a complicated site. 10 meg.
Yeah, it typically happens that we get a phone call at Friday afternoon at 2:00 p.m. oh, please send us a quote. Then we send it out. Then 3 o'clock we get a phone call. Okay, you have to be on site at Saturday. And then we deal with this client. Oh, please, can we come at Monday? So, and then at Friday next week he will have the report. I mean, or as within 5 working days. I mean, this is sometimes very like firearm work in this industry. But of course, the optimum would be to have 1 week in advance to plan to come to the site, and a few days later, the client will be a preliminary report where he can base on for his material, the orders of his material, and yes, and then it will proceed like Bob mentioned.
And next question that came in was, does the geotech study continue throughout the entire construction process? I guess this would apply for, say, larger than 10 megawatts. Do you come back at various stages of the construction process to do more study?
Yes, that happens also quite very often. That, for instance, if we have a brownfield or if we have an abandoned site with very inhomogeneous ground situation, or like the example I showed you with the bomb craters, then it was cheaper not to test every square inch of the site in advance, but to keep on the site during the construction phase and to do the quality management, so that we could avoid the concreting, and in 95% of the cases it was very cost effective for the client. And he had really a good quality control on site.
Okay, the next question came in from Andy. Do you account for the natural frequency of the racking system, or how the soil conditions may affect the natural frequency of the racking system? And have you discussed this issue with any of the major wind tunnels, such as University of Western Ontario?
Yeah, we work together with Dutch institutes who run wind tunnel testing. So we have in-house, we have several civil engineers who speak also the language of these institutes, and to work hand in hand with these institutes, so that we can, for instance, reduce the impacts, the wind impacts within the plant, so that we have higher wind loads at the fringe of the solar farm, which will result in a very cost-effective foundation engineering.
All right, next question came in from Peter. Do you recommend above-ground ballast foundation piers on landfills and/or problematic soil conditions?
Yeah, we have several options on landfills. If we have a recultivation layer that is thick enough, we will always try to set up a driven pile foundation or a helix pile foundation, but because it is much more cost-effective than concrete, and also in the end it will be much minor costs. Also, as if you have to demolish the site again after maybe a few decades, you will have not so much rubbish, and the steel is a worthwhile raw material again for the next industrial applications. So if we have enough thickness of the recultivation layer and the frame conditions are okay, then we try to use, of course, also steel piles. But if we have no other option, of course, we apply also flat spread-footed foundations. We will also apply. We will also use prefabricated concrete and elements. Yeah, we have several options, around 5 to 6 different options, and we will try to use the optimized solution for this specific location in terms of techniques and economics.
Yeah, well, the part of that question was concrete on problematic soils. It depends on what you consider problematic soils. We recently designed a foundation for caliche soils, in that we were able to actually design a foundation which leveraged the ability to undersize boreholes in the caliche and then drive a foundation into it. So in that case, the original thought was to use ballast, but drilled and driven piles wound up being a cost-effective solution. So it depends on the definition of problematic soils. as to what kind of foundation?
Do you mean maybe sulfides, that there are sulfides or sulfates in the underground, or which kind of problem do you see or do you think about?
Yeah, so what's the definition of this person's problematic soils?
And let's see, they didn't specify problematic soils, but Peter, if you wanted to chat in the meantime, I'll go on to the next question. From Albert, what countries do you work in? Specifically, do you work in Mexico?
Yes, we work out in Mexico. We work in Middle America, South America, Africa, Asia, Southeast Asia, Japan, and as in, of course, North America, Canada, US included, and yeah, everywhere. Also, I think the only continent we had only one project so far is Australia. So we have around 200 to 250 projects each year worldwide. Also in Mexico, Nicaragua, French Guiana, Chile, and so on. Brazil.
Great. Next question was from Stephen. As a project engineer for a solar developer, I hire geotechnical engineers, civil engineers, and I rely on structural engineers from various racking suppliers to provide third-party engineering services. We typically initiate geotechnical investigations before a racking supplier is selected. Is it still valuable to perform pull tests during the overall geotechnical site characterization at the start of the project development, or is it better to wait until to decide on a racking solution for initiating pull tests?
It's definitely better to start with pilot tests also early in this stage, and we did many times also load tests on the same site with different piles, and we're also able to recalculate load tests to apply it for different racking structures and different manufacturers. So, for instance, if we get an order to make that load test for a feasibility study or for the first exploration, and if the client says to us, we don't even know yet the mounting system, the final system we want to select, we want to subject this to a bid, then we take care about that. We will keep our expertise and our load testing so general that every mounting structure manufacturer can use our expertise for its own design, and then it will be very cost effective, and they will have only very few uncertainties left compared to a very general soil expertise that delivers only friction angle, unit weight, and cohesion, which is not sufficient to do a final pile design and to do a final quote.
So let me add something to that, and that is doing the geotech first, and along with the load testing, actually is much more cost effective than simply being able to use the load testing for any racking company. Because by the time we've been on your site and done the load testing, we can come back to you and tell you what's the most cost effective rack geometry to use out there. The soils drive the foundation requirements. Certain racking types have certain foundation limitations. If we know what the soils are and have measured the bearing capacity, then we can go back to you and say, to optimize the cost of installing a foundation racking system, your racking geometry ought to be X or Y.
Yes, I completely agree with you, Bob. And it's also very cost effective in that term that we address also the soils already. When we do load tests, our report will also include all the information you will gather by a conventional geotechnical report. Because if we draw out the piles from the soil, from the underground, we will address each layer, the spatial layering also of the soil. So this information will also be included in our report, and you have only one team coming to the site, and because if you have, for instance, 5 bidders that they are able to submit the final and the binding quotation, they will also have to send out a geotechnical team doing load tests. And then this cost of these 5 teams will be, in the end, will be added in the final quotation, because if a company has to do 5 bids on projects and wins only maybe 1 time, and it has to send out 5 times a geotechnical team, the bid will be higher, of course, the quotation will be higher, including all the pre-costs of the several bids and projects. So it's much more cost-effective if the building owner prepares its own load test report by an independent engineering office, and if you provide all this information already ready to bid on for all bidders.
Let me add one more thing. One recent experience I had, once I'd done the load testing on the site, I was actually able to work with the racking company to optimize the foundation design for the racking. And the process leveraged the racking system's own design characteristics to reduce the foundation length by just enough, so that we went from a 300% cost of rack installation or foundation installation to 100%, just reducing the foundation length by 1 foot. By optimizing it for the rack with the help of the racking company, we were able to reduce the foundation installation costs by 200%.
Excellent. Next question came in from Stephen, and this is specifically for landfills and landfills where the cap cannot be penetrated. So the question is, for landfills, what type of geotechnical analysis should be performed, assuming that there is no subsurface exploration because the cap cannot be penetrated, but are there other site characterizations recommended?
Yes, of course. There you should perform a conventional geotechnical exploration, including enough exploration points, because what we have experienced also is that the thickness of the recultivation layer may vary. If you start the investigation at the bottom of the landfill, you might have higher thicknesses than if you end up at the top of the hill. So to avoid any damage to the sealing system, to drainages and sealing layers, you should perform enough exploration points, of course, to determine the thickness of the recultivation layer. And furthermore, of course, to be able finally also to do a slope stability analysis depending on the slope angle. Sometimes you have also, of course, waste or landfills that are that are not very steep. But if you have slopey, as a slopey mountain shape, of course, also you should think about the slope stability and the stability of the whole landfill, because wind loads will be also induced by your mounting structure. So you should consider also a slide on the sealing layer, for instance, because between the geotextile, the geomembrane, and mineral layer, you have a very low friction angle, and this all should be considered in such an analysis.
Okay, and we have 2 more questions for those that have stayed on. Thank you very much. The next question is from Gary. Are load tests done in accordance with an ASTM standard?
Yeah, we include this ASTM standard, but we do we gather additional information. For instance, we do cyclic testing to determine exactly the point where the plastic deformation grows over elastic deformation. So we include ASTM standard, of course, but we put also our emphasis on the specialities of solar-specific piling and pile foundation engineering.
Okay, and there was a follow-up question from Gary about the previous question regarding landfills. So in that case, were you suggesting that you should are you suggesting to drill borings through the landfill cap and liner?
Oh, that it depends from the thickness of the recultivation layer. If the thickness is small enough, sometimes we work also with our hands. We just dig a hole with our hands or with a small excavator that delivers more information than just drilling, and is less harming and less risky to the surface liner, because you see always where you're digging, and so it's less harming to use your hand or a small excavator with a shovel without any teeth.
Yeah, both Jürgen and I have worked on landfill closure design, so we're very, very well acquainted with the issues of protecting the impermeable layer, the barrier protection layer, and the evapotranspiration layer. The point Jürgen is making is that we know enough about landfills to protect the layer while doing the geotechnical investigation and deriving enough data for enough points on the landfill to fully understand how the capping system responds to various geotechnical, driving forces from racking system.
All right, and I think this is the last question. Is there a ballpark estimate to use about how much should be spent on geotech? I'm looking for either $1 per megawatt or a % of total cost basis.
Well,
gosh,
because I think it's
yeah, the cost of geotech and foundation design is so small compared to the overall cost of project execution that and the conditions of various sites differ so radically that it's not very useful to actually try and figure out a typical cost. I will say, however, that on small projects, up to 2 meg, it's possible to get a solar-specific geotechnical site assessment, depending on the location and the complexity of the site, for $10,000 to $15,000, and those prices can be, $30,000 for a 10 meg site. It really depends on the amount of time that ultimately we have to spend on site doing soil exploration and load testing. But if that helps a little bit, those are some reasonably typical figures.